Pause. Imagine you toss an apple into the air. You expect it to slow down, stop for a moment, and fall back into your hand. Gravity is reliable that way. Now imagine you toss that same apple, and instead of slowing down, it speeds up. It accelerates away from you faster and faster, heading for the clouds and beyond. You'd be pretty confused, right? You would question everything you thought you knew about the laws of physics. Well, in the late 1990s, that's exactly what happened to astronomers. They were looking at distant exploding stars called supernovae to see how much the expansion was slowing. Everyone thought gravity would be putting the brakes on everything. But the universe had a surprise for us. A big one. The expansion of the universe is accelerating, pushed by something we now call dark energy. If you ask someone what the universe is made of, they'd probably say stars, planets, gas, and dust. They wouldn't be wrong, but that's only a tiny slice of the picture. All the atoms in you, me, the Earth, and every star add up to less than 5%. It's humbling. We're a tiny bit of fluff in a vast dark sea. The rest is dominated by two invisible components. About 27% is dark matter, and roughly 68% is dark energy. Dark matter clumps and builds structure. But dark energy is smooth and acts like a repulsive gravity on the largest scales. On solar system and galactic scales, gravity wins easily. Between galaxies, that gentle push adds up. About 6 billion years ago, dark energy overtook matter, and acceleration began. The answer lies in Einstein's general relativity, our modern rulebook for gravity. Gravity isn't a force pulling at a distance, it's the curvature of spacetime caused by energy. Objects follow those curves, the straightest possible paths in curved space. In GR, both energy and pressure gravitate. Positive pressure helps pull. Negative pressure, tension, pushes space to expand. Dark energy seems to have positive energy density and strong negative pressure. As space grows, its dark energy density stays roughly constant. So expansion creates more space, which carries more dark energy, which drives more expansion. In the early dense universe, matter's gravity slowed expansion. Later, dark energy took over. That's the key to a runaway universe. Measured across billions of light years, we see that push clearly in the data. In 1917, Einstein added a term, the cosmological constant, lambda, to hold a static universe. It was a repulsive energy balancing gravity, a mathematically allowed, not required option. Then Hubble discovered the universe is expanding. Einstein called lambda his biggest blunder, and for decades, most assumed it was zero. In 1998, supernovae revealed acceleration. Suddenly, L was back. A very small positive lambda acts like constant energy with negative pressure. Exactly what we observe. His blunder may be his greatest accidental prediction. Today, LCDM explains the CMB, galaxy clustering, and more. Simple, predictive, and successful. The discovery of acceleration earned the 2011 Nobel Prize in Physics. While lambda fits beautifully, it hides a giant skeleton in the closet. Quantum field theory says empty space seethes with virtual particles. That activity gives the vacuum an energy, uniform, with negative pressure. On paper, it looks like the perfect match. But calculations predict a vacuum energy about 10 to the 120 times too big. Not a small error, the worst theoretical prediction in physics. Something deep is wrong. QFT, GR, or both. We call it the cosmological constant problem. Maybe an unknown principle cancels almost everything, leaving a tiny residual. We don't know what that principle is. It's a mountain balanced on a needle. Some propose dark energy is not constant, but a dynamic field called quintessence. Like a field, somewhat like the Higgs, with energy that evolves in space and time. Unlike lambda's constant density, quintessence can change. It could solve fine-tuning, high early energy decaying to today's tiny value. If L is right, acceleration continues steadily. If it's quintessence, the future is open. It could weaken, slowing acceleration or stopping it, or grow stronger, phantom energy, leading to a big rip of galaxies, stars, even atoms. Missions like Euclid and the Rubin Observatory will test whether dark energy changes over time. Any sign of evolving density would upend L and point to a new force of nature. What if there's no dark energy at all, and gravity itself changes on huge scales? GR works perfectly nearby, but maybe not across millions of light years. Enter modified gravity. On vast scales, gravity could weaken or even turn effectively repulsive, then acceleration is baked into new gravity laws. But any new theory must pass GR's tests in the solar system and explain gravitational waves. Many proposals fail, predicting wrong structure growth. We compare expansion history to how structures grew. A mismatch could implicate gravity. Probing gravity on cosmic scales is a frontier of 21st century physics. So far, Einstein plus dark energy still wins, but we keep testing. They share a name, but they're totally different. Dark matter pulls, dark energy pushes. Dark matter has mass and gravity. It clumps into halos and builds galaxies. We infer it from its gravitational effects on what we can see. Without it, galaxies wouldn't have formed as they did. Dark energy isn't matter. It doesn't clump, it's smooth and uniform. Its negative pressure pushes galaxies apart. Early on, dark matter built structure. Today, dark energy stretches it. Dark energy's density stays roughly constant as space expands. Some speculate a link, but there's no evidence, so we treat them separately. What do we know? The universe's expansion is accelerating, confirmed by distant supernovae, the cosmic microwave background and large-scale structure. Dark energy makes up about 68% of the cosmos. It has strong negative pressure and doesn't clump like matter. Its density has been constant or nearly so for billions of years. These facts underpin the remarkably successful Lambda CDM model. What don't we know? What dark energy actually is? If it's vacuum energy, why is its value so tiny? That's the cosmological constant problem. If it's a dynamic field, what are its properties and origin? Or does gravity itself need an upgrade? For now, we just don't know. The discovery of dark energy reshaped our view of the universe, past, present, and future. If Lambda rules, distant galaxies will slip beyond a cosmic horizon, leaving us increasingly isolated. One day, the night sky may look nearly empty. Future observers might think their galaxy is the whole universe. We are privileged to live in a time when the evidence is still visible. It's not a reason for despair, it's a call to curiosity and wonder. Every new telescope and sky survey turns another page of the cosmic story. Dark energy links the smallest scales of the quantum world to the vastness of space. Solving it may require a new synthesis of gravity and quantum physics. The universe is stranger and more magnificent than we imagine. Thanks for watching. Like and subscribe. Stay curious.